Alright, so let's talk 5.2, number 33. So we have an equation a y double prime plus by prime plus cy is 0. So we have a, what is this thing?
Second order.
It could be a Dirac-Odom, or it could have.
No, it's totally a Dirac-Odom.
Constant coefficient.
This is,
Oh, but are A and B, they are constant coefficients.
yeah, a, b, and c are constants here, so if a, b, and c are constant, yes, they are, then this thing is a Schwankelschote.
Are constants inclusion, if that's a word, non-real numbers?
Yeah, so the constants in this class are assumed to be real numbers.
Bummer. Would it work with non-real?
It gets just a little bit more complicated, but not a lot.
Okay.
You just have to know some things about complex arithmetic, basically.
Cool.
Specifically, in this case, you are supposed to note that this thing has a repeated real root R1. Oops, sorry, not this thing, but the associated characteristic equation. So the associated characteristic equation is AR squared plus BR plus C is 0. Right? After subbing in a guess and dividing. So this thing, they tell me, has a repeated real root. Okay. And that takes just a second. You have to think all the way back to, like, I don't know, algebra 2 or pre-calculus maybe?
A week ago.
R plus something, plus or minus something squared equals
0.
Yep.
Oh, yeah, so you're like, wait, hang on.
C is nothing.
What does it mean to have a repeated real root? That means that in the quadratic formula you get 0 under the square root, right?
Yeah. So b squared minus 4ac is 0.
Yeah, so you get something that looks like this. You get negative b plus or minus square root of, that shit's 0, over 2a, right, is r. Okay, so this gives me an explicit formula for what that r is. That's r1, right?
Yeah.
You guys with me? So, another way I could do this is I could factor out an a, and then think to myself, that's r squared plus something, r plus something else,
Yes.
right? And then you'd be like, oh, hey, you can factor stuff like that usually, right? Like,
Yeah.
in a good world, you can factor. So you'd get something like r minus r something, and r minus r something is 0.
That's repeated.
Yeah, the fact that it's a repeated root tells you that those are the same thing. You guys with me? So I know that I can rewrite this thing as a times r minus r1 quantity squared is 0.
Why do you want to factor out an
Why do you want to factor out an a? Why do you have to factor out an a?
You have to, so you get it in that form.
Yeah, you have to factor out an a to get it to here, so that this can be r minus something times r minus something. And actually, you're not even guaranteed this, except that you know this has a real root. Right? You guys see that? It's not a complex conjugate pair. If it was a complex conjugate pair, you might be SOL on factoring this over the roots. So, I know that I can rewrite this that way. That's what having a real root says. And then, part A of this problem actually says, I am supposed to think of e to the rx as a function of two real variables, r and x. So I'm thinking maybe phi as a function of r and x is e to the rx. Normally I only think about this as a function of one variable, right, x. And then I take derivatives like I'm taking derivatives in Calc 1. This would force me to take derivatives like in Calc 3, right? So I'm looking at this and they're like, they claim that I should be able to show that a times the second partial with respect to x of e to the rx plus b times this first partial with respect to x of e to the rx plus c e to the rx has to look like, so this is the thing I'm trying to show, right? So they're saying this has to look like a times r minus r1 squared times e to the rx. And I'm like, huh? Well, shit, I don't know. I can take derivatives, right?
Well,
So partial with respect to x of this thing is
r squared,
Combusts down into your.
ar squared, e to
So you
the
got
rx.
ar squared e to the rx, right? Each derivative with respect to x kicks an r, plus a br e to the rx, plus a c e r to the x.
Oh, b's is gone, and then you're left with a and stuff
Okay, and then you can factor out an e to the rx, right?
for both sides.
So that was calc 3 to there, factor to here. So I got e to the rx, a r squared plus br plus c, right?
And then you pull from previous.
Yeah, I know.
And then I
Yeah.
know that I can rewrite this thing here that way
Right.
because it has a repeated real root. So I do that and check. So this line is because R1 is a repeated real root. You guys with me on this? Okay, so that's part A. Part B, differentiate B with respect to R to obtain something. Okay, so let me write the equation that they were talking about now. So the equation that they're talking about is literally just the beginning and the end of that. So, oh, conveniently those are on the same line already, so I'll work over here. So they're like, alright, here you are, that's part B. Go out and hit this whole sucker with a partial with respect to R. Okay.
Probably should have left the bottom then, huh?
So,
Super easy.
yeah, this isn't actually even really particularly hard. They want me to leave all the derivatives on the left-hand side. Well, almost all of them. So, I got
2AR.
A, and then the partial with respect to R of whatever the partial with respect to x done twice of e to the rx is, plus B, partial with respect to R, partial with respect to x of e to the rx, plus C, and then that one I actually know how to do, right? Close. You're differentiating with respect to what? R. And so this kicks a an x e to the rx. Right, you get e to the stuff times the derivative with respect to r of the stuff. And then on the other side, oh, and this is where things get whackadaisical.
Well,
I gotta-
It's just gonna be 2A times R minus, the quantity R minus R1.
2a times r minus r1, good.
So either or.
So that was the derivative of the first thing,
Right.
times the second, plus
A quantity R minus R1 squared times, or AR.
ar minus
AX.
ar minus r1 squared.
Right.
Right, that's the first thing, times the derivative with respect to
R, so.
r,
Slap an X in
E
there.
to the
so
RX.
x e to the rx. And then they want me to notice that you can factor that out a bit.
Oh, really?
So you're like, alright, what's in common between those?
A.
Well, there's an a
R minus
and
R1.
e to the rx's,
What about the R
And then R minus 1.
and one r minus 1,
R minus 1.
or r minus r1.
Because I'm just gonna node factor all that crap out.
And then you're like, alright, so what's left in the first term here?
2.
I took care of that and that and that, so a 2. And then in the other term here,
We have another
I took
R.
care of that and one of those and that.
So 2x and then
So there's a
R minus R1.
plus and an x and an r minus r1 left. And I think that's exactly what they wanted me to see.
Why would they want you to see that?
They wanted me to see that. So, okay, so I was supposed to see this. Like, I don't know, that's what they said to see. So, check, I've done part B. Part
Didn't
C
you want us to do
says,
the left side?
yeah, so part C says, reverse the order of the partial derivatives in the first two terms on the left side to obtain something. Okay?
Could we just say by the properties of numbers and partial derivatives that we already know this would be true?
Is that even, oh, that's totally fine, you can do that.
So, you can do that as long as the functions are continuous enough. And it's really hard to believe that e to the rx isn't a hella nice function, right? So, okay, I believe that I can flip the order of integration. That is something that a mathematician would be obliged to check is true for this kind of function, and an engineer would just go.
Nice.
So, if your intent is to be an engineer, hit me, just flip them, it's fine.
Sweet.
So you got here an a partial with respect to x done twice of the partial with respect to r of e to the rx plus b partial with respect to x of the partial with respect to r e to the rx, and then that one we already did, so that's just c x e to the rx.
Would I ever run it into any of this stuff as an engineer? Like something maybe potentially?
Oh, something like this?
Yeah.
Basically what they're trying to get you to realize here is that the solutions, that adding the x trick, like that's the punchline of this problem. So, yeah, this shows up when you're critically damping, right?
So,
Remember the trick for repeated real roots, right?
Oh, adding the T.
Yeah, you're like,
Oh,
okay,
gotcha.
so my homogeneous
Yeah.
solution for this thing would be C1 e to the R1x plus, and then C2, and I'd normally just go like e to the R1x again,
But you need the other
but
X.
that's not linearly independent, so they'd throw that x on here. And this x is the thing that they're trying to get you to see in this problem.
Show you where it came from, basically.
Yeah.
Gotcha.
Yeah, yeah. So,
Came from all
kinda.
this crap.
So you switch the order, and then we can actually do these derivatives, right? So I'm going to play a little fast and loose and just erase stuff, because
So-
it'll make my life a little easier.
you said reversing the order. Do you mean like slapping a partial with respect to x to the whole function? Or
No, I mean just these two things happen, right? The
The other
order
way.
in which these happen, you do x's derivative twice, and then you do r, versus this thing where I do r first and then x twice.
so we're leaving the right hand side of the equal sign alone.
Yep, I'm leaving the right hand side alone, because they said to.
Remember Calc 3 how we could like switch the steps of integration?
Yeah, what's that?
Yeah, no.
So
Oh,
what's
isn't that,
what's it
uh,
called when you switch them?
Whatever.
There's
we
a
want.
theorem for that.
Close,
It's
Yeah.
Clairaut's. And so you need to check the thing for Clairaut's, right? You need the partial derivatives to be reasonable, and here they are, because e to the rx is killer nice.
Unless r is tangent.
R's a variable, it's r.
It's hard.
Yeah, stop that.
So here I should be able to do these derivatives, right? So the partial with respect to r of e to the rx is
X e to the rx.
x e to the rx.
Oh god,
And this is why I'm erasing, because I'm going to have some product rules ahead of me.
what's up? We have like 8.
And here you have an x e to the rx. Okay, so now you need two derivatives of this thing.
So e to the rx plus.
Wait, let me just do that over
Doesn't
here.
it follow Pascal's triangle?
Okay, so just over here in the margin I'm differentiating, right? So I'm like, alright, so one derivative's gonna be first thing
You need more room than that.
times the derivative of the second,
What's your respect?
and I'm with respect to x again, which is really the hard part, and then plus,
The other thing.
The same, it's
just
just
e to the
times
RX.
e to the rx, yeah.
it's just an e to the rx. Okay, and this isn't so bad, so now I need to differentiate it again, right?
With respect
So I'm like, okay,
Getting the
so
same thing,
So
whether
pi
you do
roll
X.
inside of.
first function, leave it alone.
Well, we already know what that first thing's gonna be, so we do that.
Oh, it's gonna be that times an R, right?
Right.
So yeah, you could add that. You'd be like, alright, I know this first one. It turns into R times that crap. Is with me?
Plus R.
Right, cause this is just the same thing I had before with an extra R on it, so I took the R out. So I got that, and then there's a plus,
R.
and then I need a derivative of that, which is R e to the Rx. Okay, so I got A times, and all this jazz, there's two R e to the Rx's, and an XR, so there's XR e to the Rx, plus 2R e to the Rx.
Isn't that R squared? X?
Yes, it is. Thank you. In the first term. Thanks. And then I have a plus B. Oh, and I know the derivative of that thing. I had to do that over here. So you just plug it in. So you got a B times XR e to the Rx plus e to the Rx.
Yeah.
Yeah, this is why it's not fair that the prerequisite for this class is Calc 2.
Half the proof
I mean, it's not like this is the hard part.
Required Calc 3 to do.
No, I do have to, when I have a student who hasn't had Calc 3 in here, I do have to spend a minute and teach them how to partial differentiate.
It's not.
But that's it, like, partial differentiation is not the hardest thing in Calc 3,
No.
right? Not even close.
It's like the first week.
Yeah, it's.
The rest of it.
Okay, so I did this, and then I'm supposed to notice,
Oh, yeah.
Factor, can you factor some stuff out again?
oh bugger, I didn't have to do that.
Fucker.
Too late.
That's
Shit. I did that. I was supposed to get to here.
That's it?
That's part C.
Oh.
And then part D says, set R equals R1 in B and D.
What?
Okay,
I know. R equals
in
R1.
B and D. So
Why they just-
this thing
You're gonna
here,
assign this as homework.
There's no D in here.
this was B,
Yeah, what the hell is D?
and this was D.
Okay, set them equal to each other?
So I'm supposed to set R equals R1 in there.
Is C just not a thing anymore?
So if you set R equals R1,
So make that 0.
this, on the right-hand side, you get 0, right?
Oh, I see what you're saying.
And then that's the homogeneous.
So if you do R equals R1, that puts 1, 1, 1 there, and this whole piece zeroes out.
That's the homogeneous.
Okay, so this is from B, right?
Sure.
That's one of the solutions. I know that because it satisfies the differential equation. Okay, in D, if I set R equals R1, I got an R1 there, an R1 there, and an R1 there, and over here you get
0.
0. So I found out that over here, the function I'm differentiating is this guy. See that? So that tells me that XR1 is the solution. You guys see that?
So this is how they figured that out, eh?
Yeah, this is how you would figure that out if you weren't just groping around in the dark, right? Like, it seems like a reasonable guess to make, but there's a good reason that it works still. And it's really because of Clairaut's theorem, right? See that?
Interesting.
So this is one of those kind of cool things, like every once in a while you'll find some guess that seems kind of justified, and then you like explore why it works and you'll end up back at some fundamental theorem from Calc 1 or 2. And be like, whoa, cool!
My old friend.
So yeah, here's, welcome back to Clairaut.